Welcome back, analyst. So today we're diving into this explainer on the SASB standards for the iron and steel sector. We're tossing out the fluffy sustainability narratives and getting straight to the exact quantitative metrics required for reporting water and waste management. If you want to know exactly how to measure, assess, and compare a steel producer's environmental risk profile with absolute precision, you are in the exact right place. All right, let's get right to it. Here's our roadmap for today. We'll touch on steel's core environmental risks, look at water withdrawal versus consumption, and calculate baseline water stress. Then we'll track total waste weight, categorize hazardous and recycled waste, and wrap it all up with the essential takeaways for your analysis. Starting off with Section 1, Steel's core environmental risks. The standard explicitly notes that entities face increasing operational, regulatory, and reputational risks associated with water scarcity, and that the industry generates significant quantities of hazardous wastes. Look, as an analyst, you already know these aren't just feel-good environmental talking points. These are massive, bottom-line financial liabilities. We're talking severe production halts if a plant runs dry, hefty fines for mismanaged waste, and crazy high costs for water acquisition in stressed regions. That's exactly why SASB requires such rigorous tracking here. You literally can't manage what you don't measure, and you definitely shouldn't invest safely in what isn't measured properly. Which leads us to Section 2, water withdrawal versus consumption. Okay, first things first, stamp this unit into your brain right now, 1,000 cubic meters. Whenever you're digging into an iron and steel producer's SASB disclosures, both total water withdrawn and total water consumed have to be reported in thousands of cubic meters. If you see it in gallons or just single cubic meters, well, the data hasn't been standardized to the framework. You've got to master this unit because it's literally the foundation of all your comparative analysis. Now, what's really fascinating here is the explicit difference between these two categories. Withdrawn is basically all the water pulled into the facility. We're talking surface water, groundwater, collected rainwater, municipal supplies, the whole shebang. But consumed has a much, much stricter definition. Consumed water is the water that never makes it back to its original source. It's the water that evaporated during those intense heating processes, water that actually got physically incorporated into the final product, or water that got discharged into the sea instead of the original freshwater catchment. Pinpointing this gap tells you exactly how efficient a plant's closed-loop water recycling systems actually are. Moving right along to Section 3, calculating baseline water stress. Because, it's not enough to just know how much water a company uses. You need to know exactly where they're using it. SASB requires a highly specific three-step calculation here. Step 1, the company analyzes all their operations using the World Resources Institute's Water Risk Atlas, often just called Aqueduct. Step 2, they identify locations categorized as having high baseline water stress, meaning 40 to 80% stress, or extremely high stress, which is anything over 80%. And finally, Step 3, they calculate and report the exact percentage of their total water withdrawn and the percentage consumed, specifically in these highly stressed regions. I mean, think about it. If 90% of a producer's water consumption is happening in an extremely high-stress zone, your risk model needs to be flashing red for potential supply disruptions and price volatility. All right, let's pivot from the input side over to the output side with Section 4, tracking total waste weight. Just like we locked in 1,000 cubic meters for water, let's firmly establish the baseline rule for waste. Unlike water, waste generation is always tracked and reported in metric tons. The steel industry creates an absolute mountain of byproducts, and this metric covers everything solid: slags, dusts, sludges, scrap steel, and used oil. When you look at the exact SASB metric code for this, EMIS 150A.1, I want to remind you that we are strictly looking at solid waste. SASB explicitly excludes gaseous wastes from this particular metric. Those get handled over in air quality and greenhouse gas emissions. For this code, if it's solid and the entity discards it, it gets weighed in metric tons and reported right here. That brings us to Section 5, categorizing hazardous and recycled waste. Think of a company's total waste in metric tons as a giant donut chart. SASB requires producers to slice that total weight into very critical percentages. Basically, what exact percentage of that total is classified as hazardous and what percentage is successfully recycled. This is absolutely vital because process wastes like electric arc furnace dust are heavily regulated hazardous materials, mostly due to their heavy metals. If a company is sitting on a huge, unmitigated percentage of hazardous waste, they're staring down the barrel of massive disposal costs and serious long-term liabilities for contaminated sites. But we also need to demystify the strict rules around that recycled slice of the pie.
SASB does not let companies greenwash their waste data. Check out these exclusions. Yes, recycled waste includes materials that are reused, remanufactured, or sent externally to a third party for recycling, but it explicitly excludes any landfill discards. And actually, scratch that, this is a huge trap for analysts. Material that gets incinerated explicitly does not count as recycled. Even if the facility burns the waste for energy recovery to power their plant, under SASB standard, no way, that is not considered recycling.
All right, let's wrap this up with Section 6, Essential Takeaways for Analysts. So what's the main takeaway from all this? Well, your financial models are really only as good as the data feeding them. You absolutely have to master the units, thousands of cubic meters for water and metric tons for waste. You need to rigorously apply those SASB definitions, knowing exactly the difference between water that's just withdrawn and water that's permanently consumed. And finally, utilize that WRI aqueduct tool to pull those exact water stress percentages alongside the strict percentages of hazardous and recycled waste. This granular data is your ultimate shield against overlooking those hidden operational and regulatory landmines in the steel sector. I want to leave you with this final thought to chew on the next time you open up a sustainability report. If an iron and steel producer can't accurately measure their exact percentage of water stress or cleanly categorize their hazardous waste today, how are they possibly going to survive the operational bottlenecks, the water shortages, and the aggressive environmental regulations of tomorrow? The data tells the whole story. You just have to know how to read it. Thanks for joining me on this explainer, and happy analyzing.